what we did yesterday to these three cases. Okay, and this will be joint work with Frederick Palesi, Sir Tan, and Sean Lawton, all the cases. So, and I'll do briefly a brief, very overview of the motivation. Sorry if you were there yesterday, you have seen this already, but I just want to recall the notation that we use, and for the people that weren't yesterday, introduce it. So we have a group, gamma, and a Lie group G. And we consider representation from gamma to G up to conjugation. So that's what we call this Matt-Freck call. And we look at the action of the outer automorphism on the outer automorphism group of gamma on this character variety. And yeah, so I keep calling it character variety. It's not a variety as I define it, but for the dynamical problem that we will answer today, it doesn't matter. And so the main question that we will discuss is that what can we say about this action? And in fact, today we will focus much more on how can we build domain of discontinuity for the action. So open sets invariant under the action where the group acts nicely, properly discontinuously. And just to give very two points of motivation that explain how much the story is not really understood is one point I wanted to make is for you to try to keep in mind a sort of dichotomy between compact group and non-compact group. So compact groups in general, or in the cases known, this action is chaotic, is ergodic. And the non-compact group on have domain of discontinuity. So today we will mostly remain in this setting. Actually, we will remain in this setting except from this slide. And maybe again, one thing that I hope you will keep in mind from this talk is that where this domain of discontinuity come from, they really come from geometric structures. So, and we will have different geometric structure that might have the same underlying group gamma. So, okay, so, and today we will really be in like these settings for the first half of the talk, and then G will change in the second half. But even in this setting of SL2C, the story is still mostly not completely understood. So, and here again, I want to show a dichotomy between the behavior for closed surface group and the behavior for free group. So for closed surface group, we know by a theorem of Fricke that the mapping class group acts properly discontinuously on convesco compact representation. Remember, convesco compact are the representation for which the orbit map of the group in the symmetric space associated to the group, so into H3, is a QI embedding, and also correspond to the interior of representation that are discrete and faithful. So injective representation such that the image is discrete. And the conjecture is that outside of this set, the action is ergodic. So this is the maximal domain of discontinuity. But it's still open. And so in this setting, it seems that we have a dynamical decomposition, proper discontinuity, ergodic, and a geometric decomposition, discrete and faithful, and non-discrete and faithful. And these two decomposition, at least conjecturally, they are the same. On the other hand, we'll see that we have seen yesterday that for the free group, this is not the case. So again, we have a geometrical decomposition in discrete and faithful and non-discrete and faithful. And again, we have that the outer automorphism group of Fn acts nicely on this Convesco compact or Schottky representation, but Minsky show that there is a bigger domain of discontinuity where out Fn acts properly discontinuously. And so then yesterday, we mostly focus on the action of the mapping class group of the one-hole torus on the character variety in SL2C. So what we will try to do today is we will try in the first part of the talk to change the one-hole torus with two other surfaces, like the four-hole sphere and the three-hole projective plane. So we will see when non-orientable surfaces come into play, how things change a little bit. And these two surfaces, they have a common fundamental group F3. And so while we discuss those two surfaces, we will have to see how to parameterize the character variety from F3 in SL2C. And then in the second part of the talk, we will try to see what happens when we change the target group. And so, in fact, for this work, initially we were thinking about SL3C, and actually we couldn't really develop the right setup to conclude in the SL3C case, and I'll try to explain why. But we were able to say something for SU21. Please, like yesterday, feel free to interrupt me at any time. If I don't see your hand, just yell at me. Okay. Okay, and so yeah, the result today is a joint work with so the first part, case A, is with Frederick and Sir Putin. Case B is just with Frederick, and case C with Sean and Frederick. And again, what we build the domain of discontinuity for the action of the mapping class group. Remark for the first two cases, differently from yesterday, this mapping class group now is not a finite index in out F3. Okay, yesterday we had this, this is something that happened just, somehow accidentally, let's say. For F2, we have that the mapping class group of the one-hole torus is basically out of. But so in these cases, these groups are much smaller. And so we find the domain of discontinuity that strictly contain the set of Convesco compact representation. In fact, they strictly contain the set of primitive stable. So here I can say also primitive stable. So it strictly contains this set, which yesterday wasn't true. Yesterday, the set that we described was in fact equal to primitive stable. Okay? Any question? Okay. So if you remember from yesterday, so at the beginning, we were setting up this combinatorial setting. So we needed to describe the curve complex. We needed to describe this equation that describe the character variety, and using this combinatorial setup to try to understand this equation, and then building up the various steps that allow us to characterize the representation that we want in terms of having this finite attracting tree. And so that's what we are going to do today. And in fact, in the case of these two surfaces, the curve complex is well understood, and the dual complex, that is what we will use, is also understood. So we'll start from there. And so, like as I was saying, like both surfaces have a fundamental group F3, and I wanted to show you how the generator look like, because that will be important, because the generator and the product of two generator or three generator are the elements that will come up in our traces. And so it will be important to understand how they behave. And so in this case, for SO4, like the three generators are the three curves that go around three holes. And the product of three of those generators is the curve that go around the fourth holes, okay? And then we have the product of two generators that really correspond to these three curves, okay? So in some sense, all these curves are peripheral, so they will not, we will not see them in the curve complex, but yeah, we need them when we want to parameterize a representation. And so here, for the three-hole projective plane, it seems that the discussion is almost orthogonal. And in fact, we will see how to make this statement that I just said precise. And so in this case, like the tree generator, we can take three generators to be three curves that intersect once. So, okay, so I'm using for this surface these two pictures. So this is really like my projective plane, and from which I remove three holes. And in this picture, I put the projective plane on the outside. So I'm identifying the boundary so that the projective plane is now here. And so these curves are now what they are called one-sided curves. They are not, so if you take an epsilon neighborhood of this curve, the epsilon neighborhood of this curve does not generate an annulus, but the way that you glue, it generates a Mobius band, okay? So the difference between one-sided and two-sided will be important. And so, yeah, the three generator are these three curves, and we have the product of two generators now corresponding to the peripheral curves. And I didn't draw it here, but let's say the curve, it will be important, the curve alpha, beta, gamma, and that curve will look like something like this. Let's see. Whoop. So again, it's a curve that intersects the projective plane three times, so it's again one-sided. Any question? Okay, so now, yeah, now let's see how the character variety look like. So you already see that the equation that describe the character variety are becoming more and more complicated. So yesterday, we only needed three traces, the trace of rho of alpha, trace of rho of beta, trace of rho of alpha beta. Today, we need 7. And so we need 7 traces that correspond to the trace of the three generators, the trace of the product of the two generators, and the trace of the product of the three. And like we also these 7 traces, they also satisfy this equation that now I played with a lot, so I can I can write it. It looks a little scary, but just think of, again, it's a quadric equation in terms of these traces. So again, the tricks that we were using yesterday of looking at the two solution when you fix everything but one will happen also here. But just one important things to notice is that yesterday the equation was symmetric in terms of the three traces, and this is not true anymore. So we will have to take care of this issue. Yeah, we'll see how we'll do that. We will have to color our curve graph. And so again, and now you see a sort of duality again, because the traces of these first four traces, are the one corresponding to the peripheral element for the foral sphere. So when we consider the relative character variety, so the character variety where the trace of the boundary curve is fixed, now what we are only left with three numbers, three complex numbers that they satisfy this equation. So you should think in this case, A, B, C, and D are fixed, any for complex number, and then the character variety are triples that satisfy this equation. And instead, for the three-hole projective plane is the other way around, the three traces that correspond to the peripheral element are alpha beta, beta gamma, and alpha gamma. And so now we fix these three traces, and so we look at four complex number satisfying this equation. Question? Okay. So again, it makes sense to consider the relative character variety because I keep saying the mapping class group, it's always the pure mapping class group. So we look at homeomorphism that fix the boundary, okay? Okay, so now how do the curve complex or this dual graph that we consider look like? Well, in the case of the foral sphere, it looks exactly the same as the curve graph of the one-hole torus. And so in this case as well, we have the identification with the Faraday graph. So you should think of this curve graph as this graph over here, this infinite valence graph. When I was a graduate student, I think Sol Schleimer was saying, you should never stop drawing. Anyway, okay, let me stop. Okay, this is the curve graph. And like yesterday, we will need to consider the dual graph. So the graph that put a vertex for every triangle and an edge when two triangles are adjacent. And like yesterday, this graph can be identified with certain ideal triangulation, what I think Tan-Yang calls tetrahedral triangulation. So again, like yesterday, what happened is that if you have, let me draw as a puncture because I think it's easier. So if you have a simple closed curve, there are exactly two arcs, two ideal arcs that are disjoint from this simple closed curve. And so if you consider the three curves that form a triangle, these give you an ideal triangulation. And what does it mean to do a flip for this ideal triangulation? You need to do a flip for both the two arcs corresponding to the same curve. Okay, and so this is a nice story that doesn't come up today, but that there is still this nice correspondence. So for the three-hole projective plane, Now it's becoming a little more complicated because the curve complex will have dimension 3. So let's see how good we are with drawing picture in dimension 3. I'll try to see if you understand my picture or try to explain them. So again, as I said, the curves in the three-hole projective plane are of two types, one-sided and two-sided. One-sided when the epsilon neighborhood is a Mobius band, and two-sided when the epsilon neighborhood is an anomalous. We will do then twist only around two-sided curves. So again, this will be the group or finite index with the group that we will consider, even if it doesn't cover the whole mapping class group. Like I started describing directly the dual graph, but maybe the way to think about the curve complex is that you first think about vertices that correspond to one-sided curves. So we have seen here with the three curves, the four curves, alpha, beta, gamma, and delta. Those are all one-sided curves that pairwise intersect once. They intersect minimally. And so what you can do is like you can put like vertices for each of these curves and put an edge between them. And then what you need to notice is that every time that you have a simple closed curve, every time you have two simple closed curves that intersect twice. So let's say we might have this curve and we might have this curve. So these are two-sided simple closed curve that intersect twice. So what you can do is that you can consider the epsilon neighborhood, the epsilon neighborhood of this curve. And so if you look at the boundary of the epsilon neighborhood of this curve, you will get two curves. One that will be homotopic to a peripheral curve, and the other that will be a two-sided simple closed curve. Like, let's see in this example, we have, we have one curve that look like this, and we have another curve that look like this. So from the pink curve, you can push this part down, and so the pink curve will be homotopic to this boundary component, and the blue curve will be a two-sided curve. And so like this explain this one-to-one correspondence between like pairs of one-sided curves intersecting once and two-sided curves. And in fact, for every two-sided curves, they come from this construction, because every two-sided curves like split the surface in two pieces that are well understood. And so if we look at the dual graph associated to this curve complex, so for every, like here, what we say is that every time you have two one-sided curves that intersect once, there exists a two-sided curves on it. And so we have this type of picture, and then we have again infinite balance for every vertex. And so for the dual graph, what do we have? So we put like vertices correspond to four one-sided curves intersecting, pairwise intersecting once. Faces now correspond to three one-sided curves intersecting once, and so on and so forth. So faces correspond to pairs of one-sided curves intersecting once, and so faces correspond to two-sided curves. And finally, three-dimensional region correspond to just one-sided curves. And so like the picture of what, so yesterday, or like for the forosphere, this dual graph was a trivalent graph. And so in this case, instead, we have as a dual graph is a four-valent graph. And so what do we have is that around each edge, we have three regions like that happen. And in fact, you should think of the picture that you had here, like this picture here, you should just bend a little bit. So the region that correspond to one-sided curve, really you should think of a banded version of the trivalent graph that we had before. And then we have faces that are these, infinitely sided polygons that correspond to these two-sided curves. Okay, so it might be so that you have a region here bounded by these three, and you have a region here bounded by these three. You have a region bounded by these three, and you have a region bounded by these. Okay. Any question? Yeah. Yeah. Yes, they are here. Like, can I erase this picture? Like, yeah, so they are exactly, yeah, like this curve alpha, this curve beta, this curve gamma, and then the curve delta. This is the gray curve. Oops. Yeah, no, good question. Yeah. Other question? And in fact, once you understood this picture, every vertex look like this picture. Yeah. Okay, so now one other piece of the story is like, okay, what is the action that we consider? And so yesterday we were considering this tree involution. So involution obtained by fixing all coordinate except of one. And so here we do the same. So in case A, like here, remember, A, B, C, and D are already fixed. And so if you fix Y and Z as well, now this equation becomes a quadratic equation in X. And so you will have two complex solution, and the sum of the two complex solution is exactly given by negative whatever multiply the X. Okay, and so the involution is exactly given by fixing the Y and the Z and sending one root to the value of the other. So the sum of X and X prime is exactly minus YZ plus P. So here I just, for simplicity, I call this quantity P, this quantity Q, and this quantity R. And then you can call the rest here by bringing this side S. And in fact, there are nice algebraic properties of the map that goes from A, B, C, and D into P, Q, R, and S that, okay, I will not discuss today, but is a nice story as well. And so in this case, for case A, we have this tree involution, theta X, theta Y, and theta Z. And again, like yesterday, the product of two involution correspond to the then twist around one of the curve alpha beta, beta gamma, and alpha gamma. So the product of these three, the product of two theta generates these trident twist, and this trident twist generates the mapping class group. So this is how we can see that the mapping class group is an index 2 subgroup of the group zeta 2 cube that we are actually considering. And in fact, we really see like the mapping class group acting both on curves and on representation. And this is part of the story that is also used. And so we do the same for case B. So now we have 4 involution, and these involution are more complicated. And again, we look at this Z2, these 4 involution that generate this group. And also in this case, up to finite index, this group correspond to the mapping class group. But the inclusion is sort of opposite, because in this case, the mapping class group really correspond to this group semi-direct product, this Z2 times Z2. So this is the action that we will consider, and I'll keep calling it the action of the mapping class group because it doesn't matter for the question. Any question? Yes. Sorry, say one more time. Yeah. So the question was, well, you keep telling us that you study the action on the character variety, and then in the slide you tell us we reduce to the relative character variety. Are you cheating us? And so, no, it's like I don't think this is a problem. It's because the mapping class group fixes all of these slices. And so, like this theory that we are building, we will discuss sometimes things in a slice and sometimes things for the global character variety, but that's not a problem. One thing that I wanted to point out, when we say this Bowditch set that we build, it strictly contain convex compact representation or primitive stable representation. That result I need to state globally, because if you fix a slice, I might or might not know if one set is properly contained into the other. So I think for that, there are some slices that I still don't know the answer. Yeah. Thanks. Other question? Oops. Oh, I think my comment moved. But what was written in this comment was that actually, if you consider the, so I'm not sure I can move this. Yeah. So if you consider, let me write it here, remark, actually, if you look at all of these 7 involution, theta A until theta Z, actually, this generates the Torelli subgroup of the mapping class group. So, these 2 surfaces, have this sort of dual behavior, and this was something that we noticed. So now I said that one problem was that the equation that we have is not symmetric in our variable. And so how do we fix it? We need to color our graph. And so what do we color? We color the edges and we color the faces. So like we want to have a coloring such that at every vertex, the three edges have three different color. And then like you color for every edge, you color the two faces that touch the edge in the same way. And so you have at every color, at every vertex again, you have the three faces around, color, three distinct coloring. And then you keep propagating. And so for the other case is the same. Now you need the four colors. And so you have, you have three regions around this edge. And so you have a pink, a green, yellow, and then you have another face here that I use purple. And then you have the blue like that. And so again, you have this four coloring. And this is what tells you which region play the role of X, which region play the role of Y, and which region play the role of Z, or in the other case, which region plays the role of A, which region play the role of B, and so on. And so now that we have this coloring, we can do like yesterday and really, like, instead of thinking of a representation in this relative character variety, really thinking of their traces, so maps from simple closed curve into C that satisfy certain relation. So again, in this case, we have for every vertex, we need the three region with their colors to satisfy now this more complicated equation. And then we have again this edge relation that reflect this. So here was what we call before P. Like these again are this involution. And for the second case, we do something similar for vertices. So we have, for every vertex, we have four regions, and so they need to satisfy the equation. For every edge, again, the two regions adjacent to the edge need to satisfy the edge equation. Again, the color is important. And here we have one more case, is that we have faces. So faces correspond to pairs of curves, one-sided curves intersecting once, and also two-sided curves. And so now these faces like satisfy this equation, because these faces, like the curve that we draw before, like if we draw alpha and beta, like the two-sided curves that we get as correspond to the element alpha beta inverse. And so the trace of alpha beta inverse, so now we use a trace relation in SL2. And so it's the trace of alpha, trace of beta, minus the trace of alpha beta. And so like E is this trace of the two-sided curves need to satisfy this equation. And so now is, again, how to translate between relative character variety and this Markov map. Question? So now, again, we can define the Bowditch set. And so I stated slightly different than yesterday. And in fact, if you read this paper, like we don't really use this point of view, but I think is nicer to state it like that. But yeah, it's the first condition is similar to what we were asking yesterday. So, oops, here there is a, what we want is that if you look at all simple closed curve, we want their trace to be not in the closed interval -2, 2, because we don't want simple closed curve be sent to parabolic or elliptic. And we want only finitely many curve with small traces. So yesterday this number was 2. Now this number depend on the boundary traces. So 2 doesn't work. So we need to consider 2 plus m, where m is the maximum of the modulus of this complex number divided by 2. And then we need to also exclude this reducible representation. So yeah, just one remark from yesterday that I think I didn't say out loud. So yesterday, we said that Bowditch was considering the case tau equal -2, and Tan-Wong-Zhang were considering all the other cases. But I forgot to say that all other tau, but you do not want tau equal 2, because tau equal 2 also correspond to reducible representation that we want to exclude. Okay, and so here, like, what do we want to exclude? Like, if you take a two-sided curve, then in this case, the two-sided curves cut the surface into 2 3-hole sphere. And so you do not want the representation that when restricted to one of these 3-hole sphere correspond to the reducible representation. And here is the same, but when you cut along a two-sided curve, like you split into a 3-hole sphere and a 2-hole projective plane. And so again, you have this dichotomy. And and in fact, this equation, you can write it explicitly because you know exactly what the traces of this element correspond, or like the trace of the generators for the two subsurface. But okay, so this is the set that we consider. And also, like yesterday, the aim would be to characterize Bowditch representation in terms of a finite edge. I didn't say the orientation on the edges is defined like yesterday. You go towards the simple closed curve with small element. And so what we want to prove is that for every representation in the Bowditch set, you can always find a finite subtree that is attracting. And once you have that, you see that the action is open, and the action that the set is open, and the action is proper discontinuous. And I wanted to say one thing that I think yesterday I might not have explained very well, since I was going a little fast at the end. So we had these 3 steps. So we had the fork lemma, and then this fork lemma was used to understand the connectivity for this region. So this region that appear here, all the simple closed curve with small traces, more complex traces. And so this will be again the first step in this case. And the second step was analyzing the traces around the region, how traces grow when you do dent twist, and escaping rays, so rays that keep following oriented edges, and they accumulate in the graph. So you want to see what happened to these rates. So, and again, like yesterday, we have that this escaping ray need to accumulate in the boundary of a trace, or in the boundary of a region with a small trace, or to not satisfy the Bowditch condition. And so I think, but the things that I wanted to point out is that when you have step 1 and step 2, actually you can really see that the Bowditch representation are characterized by this finiteness condition. So because this step 2 allow you to define this attracting tree, and this you can do for all representation, and then you can use the condition from the Bowditch set, the finiteness, to really see that in this case, the attracting tree need to be finite. And so what the step 3, so this was Jeff's question yesterday, like why do we care about this Fibonacci growth? Is that because we want to characterize this Bowditch representation in terms of the growth of the length. And so like this tells us that the length of simple closed curve really grow like the word length. And so for this, we need this Fibonacci growth. Oh yeah, and maybe like just, I will not have time to really discuss all the details, but like in this more complicated case, like what is a fork for us, we just need the 2 edges to point away from a vertex. And in this case, what you can get is that the traces of the 2-sided curve that are around this vertex, you have at least one face with small trace. And so like the idea, the bigger picture will be similar, but then you need to deal with how to do all of these analyses. That becomes more complicated. Question? Okay. So yeah, and this is what I was saying, is that from this method, you really see that you have a characterization of this set in all these different ways. So this is how we define it as no parabolic or elliptic, and only finitely many that satisfy a certain condition. Oops, here is omega. But like you can see that you can replace these with actually asking this finiteness for all the k. And also you can replace it with asking this lower bound on the growth of the length. Like the upper bound will be always satisfied, but really the lower bound is what characterizes those curves. And in fact, this is the definition that Suzanne Schlick, François Guerito's student, you heard it in Jeff's talk. These are the conditions that she considered. Yeah, and the other is in terms of the attracting subgraph. And maybe one more comment is that for the non-orientable surface, in this condition 3, you can either ask this growth for all curves, you can ask for one-sided curves, or you can ask for two-sided curves. Well, just each one of them determine the other. Okay, so if there are no questions, so the rest of the talk we will move, so we will go back to the one-hole torus, but we will change the group. And so we will see what we can do in that case. What time, how much time I have? Okay, 5 minutes. So let me choose what to say. So, okay, so maybe let me just say one piece of the story. So so when we were generalizing to this case, we initially tried to think about, we were trying to think about the group SL3C. So what goes differently when you look at this group? So in SL2C, we were using a lot the trace relation. So the fact I wrote it before, but for SL2C, like you know that the trace of the product of two matrices is equal the product of each trace minus the product of AB inverse. And so these we were using all the time, and so we don't have that anymore. And in addition, like in SL2C, you also know that the trace of the inverse is equal the trace of the matrix. And so these also we don't have in SL3. And so it was more complicated to see what happened. And so we reduced to this real form for SU21. And so for SU21, like what happened is that the trace of the inverse of a matrix is not equal to the trace of A anymore, but in this case is the conjugation of A. And so these allow us to, for every simple closed curve, because simple closed curve for us are not oriented in general, and so like associated to each region, we have both alpha and alpha inverse and all their conjugates. Like the conjugation is not a problem because this is, the trace is still invariant, but the inverse was a problem. But reducing here, we can associate the norm is well defined. But the fact that the trace relation are not satisfied anymore, it means that our method wouldn't work with this fork lemma that we would try to use. And so we need, in this case, to define this extra graph that put this what we call the edge graph. So you put a vertex for each edge, and you put an edge between two vertices if the two edges belong to the same triangle. So you get this basically like you blow up every vertex in the trivalent tree with a triangle. And so this is the graph that we consider in this context. We put orientation on this graph, and we build the subgraph, the attracting subgraph in this context. And so in this way, we are actually able to build the whole story. So let me see what I want to end up. Yeah, so I think maybe just I'll end up with just this picture here. So like, yeah, let me maybe just, oops. Yeah, so the character variety, like one important step was also the equation associated to the character variety. Luckily, in this case, we knew which generator to consider. And so you even know for SL3, and so you take these 5 traces and the traces of their inverses, and then these 10 traces satisfy 2 equations. But now already the equation become really awful, especially this second equation is a page long. So it's becoming a little untractable, but we are still in the case of SU2, because then you have this extra symmetry in some sense on the equation. We are able to really deal with what happened, and yeah, I think this is the picture that we have. So now we need to color these triangles, and so we color with these 4 coloring, and we color the curves, and in some sense we make it work. And maybe the last things that I want to finish is that I wanted to make a comment of the connection with the work of Schlick. Because I told you yesterday that what she discussed is that she studied the Bowditch set for the one-hole torus for all isometry of delta hyperbolic group. And so in particular, SU21 belongs to this category. And so like what she proves is that in this context, these also correspond to the set of primitive stable that she defined. And so like our theorem, we are able to characterize and study this set, and hence using her result, you also have a characterization in terms of primitive stability. And in fact, she discussed something similar for the photosphere that we have seen today, but for the photosphere, you need to replace the primitive stability with the simple stability. So what she calls simple stable representation. And I think it will be really interesting to her work really uses these two cases because she used continuous fraction expansion, but she used continuous fraction expansion to study the word of the element that appear. And I think with some of the tool that we have to build for the three-hole projective plane, it should be able to generalize these results to that context. And it will be really nice to generalize her result to more general surfaces not using continuous fraction expansion. Yeah, I think that's all I wanted to say today. Thanks.
Questions for Sara?
Yeah. Well, there was no relation. So in this case, what was happening is that the trace of a matrix and its inverse had the same norm because one was equal the other conjugate. And so the norm was well defined. So in the general setting, you would add to basically associate to every region two complex numbers. And when you try to define the orientation, then it becomes more tricky because you are basically saying, how do I define a positivity between pairs of complex number? And okay, one can say, look at the maximum or look at the minimum, depending on what you need. We weren't able to make it work with this way. It didn't work. And same with this trace of, so now you don't have this trace relation that connect, let's say, alpha beta with the trace of alpha beta or alpha beta inverse. But you still have some trace relation that now connect more traces. So it's a relation between alpha square beta, and then you have the trace of alpha, trace of beta, trace of alpha beta, and alpha beta inverse, and their inverses. But somehow, yeah, so it's unclear if, it might be possible to make it work, but probably you need a combinatorial setting more complicated than, so like these adding triangles that wouldn't work, yeah. Oh, yeah.
Steve, do you have a question? And if so, can you put it in the chat or? Hello, Steve. Like he was trying to say something. But I'll see if I can hear it.
Wait, Steve, if you were talking, can you try again?
Yeah.
Nothing.
Go to like another group where that happens, like SP2 or something.
Oh, no question.
Yeah, I don't know. We haven't tried other cases. I don't know if there is an equation for the character variety in those other cases. So here we were using the work of Sean that he did it. For free groups, he does for all, I I think SL3. So it might be possible. Thanks.
Any more questions?